Okay, so homework is due on Thursday. Hopefully you've started on that. It's pretty easy. Get it done, get it out of the way. That way you don't have to worry about it and you can focus on your other classes. I know you have like 15-page papers due and whatnot. So get it done. And then class evaluations, if you haven't already completed those, get online, complete that. I do read them. I do care what you say. I just ask that you use productive feedback. So if there's something you really dislike, tell me you really dislike it, but tell me why. What can be improved, what can change, not just like, I hate Professor Waite. Because, you know, that's just going to hurt my feelings and I won't learn anything from it. So I hate Professor Waite because, you know, give me a reason. Hopefully none of you hate me, but if you hate this class, I would understand. It is a difficult class, but we're almost done. It's been a good semester. And today's lecture is pretty fun. So we get to do some really interesting things or look at some really interesting things that have real-world application. Gas power cycles are maybe more familiar to you than a lot of the other things we've talked about with steam power plants and turbines and compressors and things like that, that, you know, an engine is real. Maybe you've worked on a vehicle or lawnmower and you've seen it in action. So it's kind of fun to see and understand how those work and what the differences are between different types of engines. And the lecture today is primarily just for informative purposes. There are some things of which you should take careful note, and I'll try to point those out, particularly the steps of the cycles. So if we're talking about the Otto cycle or the Brayton cycle or the Carnot cycle, you should know the steps of the cycle and then maybe how to draw it on a property diagram, because that would be a really fun thing for me to put on a final. Would be an easy one for you to get right if you have just written it on your note sheet, and easy to get wrong if you paid no attention to it whatsoever. So keep that in mind as we go through the lecture today, that there will be pictures and steps that you should take note of. If you don't get them written down completely while we're looking at the slides, these are all online. So again, final exam schedule that we are scheduled for Tuesday, May 2nd, 8 a.m. to 10 a.m. If everyone arrives early, we can start a little bit early. I'll have to make sure that the building is unlocked because sometimes people are not here by 8 a.m. to unlock it. I was locked out at 8:15 today. I guess everybody came in the back door. So let's all try to be a little bit early, get started early, and then you have just a little bit of a buffer for starting. But again, we can't start early if not everyone is here. So don't be the guy that shows up 30 seconds before time and ruins everybody else's chances. Okay, so when we talk about power cycles, we've talked about cycles previously and how we desire to have maybe a net power output. And primarily we've been focusing on these thermodynamic cycles that involve like steam as a working fluid in a power plant or some other similar situation. But today we're going to be talking a lot about power cycles that don't involve a fluid as a working fluid or a liquid as a working fluid, but involve a gas. So usually a combination of gas and air, and there are certain assumptions that we can make when we're dealing with these cycles in order to make them easier to analyze. When we're looking at them, we oftentimes provide an idealized case that we study, and we strip these actual cycles of their irreversibilities so that we can analyze it more readily. It also gives us the best case scenario, as we've talked about a lot before, and it's a starting point to get into some more in-depth analysis. So maybe the simplified, idealized property diagram doesn't 100% account for all of the intricacies of the cycle itself, but it gives us a really good place to begin and a place to compare other cycles, one to another. And although the numerical values may not be perfectly accurate, like maybe the pressure is slightly lower or slightly higher, the trends and the general concepts do carry over. So if we are reducing the compression ratio and that serves to increase the power output or decrease something else, that same trend will still carry over even though the numerical values may not be exact. But if it's a 20% increase in power output, then that generally does carry over that same trend. So again, we make these idealized approximations Now we can look at a potato, which is a structure made of cellulose and has a skin around it. It's not perfectly round. It'd be a little difficult to study if we had to model it exactly as a potato. However, we can say, well, a potato's pretty much water, so we're just going to look at this potato as a sphere of water, right? It's a lot easier to analyze it that way. Similarly, with our process cycles, we may have these amalgamous forms where there's not exactly peaks and corners, but when we idealize it, we say, okay, it doesn't really come to a stop and turn the corner here, but we're going to say that it does, and that's point 2. Okay, so we're taking these shapes that are similar and squaring them off instead of rounding the corners. So we're having distinct positions, which we can say, okay, from here to here is maybe an isothermal process, and then from here to here we're going to approximate as an isobaric process. Okay, so again, it's this idealization that allows us to study it and analyze it. So some common simplifications that we make in order to do this is the big one is that we assume there's no friction. So this can mean no pressure drops if you're talking about friction from fluids flowing through a pipe, but for mechanical systems it means there's no losses due to those forces that rub together, those oppositional forces, which if there's no loss due to friction, that means we're not generating heat, which means we're not generating entropy, right? We assume that all of our compression and expansion occur in a quasi-equilibrium way, which means that we're not compressing it so rapidly or so quickly that we're having oscillation of property values across the control volume, that the properties are still uniform as we compress and expand, and that's another simplification. Pipes and all the components will be well insulated, so we don't have to worry about heat losses. And then usually we ignore kinetic and potential energies because they're pretty small compared to any of the other energy terms that we have to consider or look at in these processes. The kinetic energy inside of an engine is not 0 because we have pistons that are moving. However, we choose to ignore that because we're so much more worried about the combustion process and how much energy is generated from that. And the kinetic energy and the potential energy changes due to these pistons moving is really small compared to those terms. So we don't need to know the speed of the piston necessarily. We often use PV diagrams to give us the area enclosed on either a PV or TS diagram will give us the network output, and then the area under that will be the heat transfer. So on a TS diagram we have heat addition and heat rejection, and it shows us at a glance how much our entropy is increasing during any single process, which gives us an idea of irreversibilities. So if we want to model a process isentropic, then it would be just straight up and down on the TS diagram, meaning the entropy is not increasing. Similarly, if we wanted to model on a PV diagram a process where the volume doesn't change or possibly the pressure is constant, then we can model those as horizontal or vertical lines as needed. And these give us, again, at a glance, we can compare cycles one to another. We can even overlay them and look at them on top of one another to see how the net power output might increase if we were to change certain components of the system or change the process slightly to a higher temperature, or maybe increase the pressure or decrease the volume. What changes will what effect will those changes have on the overall network output? And these cycles in general, we're looking for a larger network output because as we talk about gas cycle, diesel cycle, Otto cycle, these are all work-producing devices. So we're seeking to maximize the area within the curve. The Carnot cycle, we've talked about a lot before, is the best case scenario as far as reversible cycles go. It's the most efficient cycle operating between any two temperature limits. So this efficiency for the Carnot cycle, we found to be the best possible efficiency as governed by the second law of thermodynamics. And although the Carnot cycle doesn't fit our needs for a lot of the processes that we want to undergo in real life, it does, again, provide that upper boundary. So we can say, okay, What's the best we could do if it were Carnot cycle? Oh, 26%? Okay, so maybe this 24% efficient engine that I've designed isn't so bad, right? So it gives us the upper limits to what we can actually do, even if we can't ever achieve it. And the working fluid in the Carnot cycle is usually a gas or a vapor, and it's difficult to achieve that reversible isothermal heat transfer, because as we talked about before, you can either compress a gas as a liquid or as a gas, and if you try to do two-phase compression, it's very difficult, and it's also very difficult to control keeping that in an isothermal region or maintaining the temperature constant when we're operating somewhere other than the liquid vapor region. So if we're in the total liquid region, or if we're in the total vapor region, or if we're somewhere above the dome, above the critical point, it's really hard to achieve isothermal heat transfer. So again, we're just using the Carnot cycle to compare other cycles. It doesn't work for us for this process design that we're undergoing. In gas power cycles, the working fluid is a gas throughout the process, but it's a combination of many different things. The gas is vaporized as it enters the combustion chamber, and it's mixed with air, and then the exhaust gases that are a byproduct of the combustion process are also mixed in with air. So even though it's not completely air, we can make something called the air standard assumption, which we'll talk about on the next page, which allows us to analyze these gases as air. And so rather than needing to know the exact fuel to air ratio, or maybe the byproduct to combustion, needing to know the chemistry involved to determine what's actually still being vented or still contained, which hasn't been combusted completely, we just assume that it's air. Okay, so this again simplifies the process, makes it easier to analyze. So we just use the properties of air, which is an ideal gas, in order to analyze these cycles. So the air standard assumptions are fourfold. The first, the working fluid is air, which continuously circulates in a closed loop and behaves like an ideal gas. So in reality, with a real engine, we're intaking air, mixing it with fuel, combusting it, and then exhausting fuel gases. And it's not a closed cycle, it's an open cycle where we have fresh air coming in and exhaust gases going out. Well, for the idealized cycle, we're saying, let's just imagine that the air that comes in is the same air that just left, because we're not worried about how much fuel to air ratio there is or what's in the exhaust gases. We're just calling it all air. So we're just going to assume that it's the same air. All the processes are internally reversible, so we've eliminated friction. We're assuming it's quasi-equilibrium. We're not worried about heat transfer to the surroundings. And then with the combustion process and the exhaust process, rather than needing to know some specific mass balance and stoichiometric ratios to determine what's coming in, what's coming out, we just say, okay, instead of worrying about the mass that's coming in, we're just going to assume that we're replacing these processes with just a heat sink. Okay, so a heat sink and a heat source. The combustion process itself, we say, is just like a heat addition process. And then the exhaust process, we say, is like heat removal. So we're intaking, or we're exhaling, exhausting hot gases. We're saying that's like heat is being removed from the system. And the combustion process itself, we say, is like heat is being added rather than needing to know the chemistry involved. So these four assumptions, if we're undergoing a process that relies on these four assumptions, it's said to be operating on the air standard cycle. And one additional assumption that we can make, or simplification, is that we're going to use the C sub P and C sub values at room temperature, which makes it the cold air standard assumption. So rather than needing to know the temperature of the exhaust gases or anything like that, we just say, okay, we're assuming it's air at room temperature. This is the cold air standard assumption, and that's how we're going to analyze this device. And again, it's an idealized version of what's actually happening in the system. But if we're analyzing all of our designs that way, then we can compare them one to another, and the same general trends will apply. So if this one is a greater work-producing device, using these air standard assumptions, cold air standard assumptions, then it still will be when we actually have fuel and exhaust gases involved. That the mechanisms that make it good don't necessarily rely on the temperature of the fuel. Okay, so more terminology for reciprocating engines. We have top dead center, TDC, which is the position of the piston when it's at the smallest clearance volume. Okay, so top dead center is when the piston is here. Bottom dead center is when it's at its maximum volume. The stroke is this linear distance between top dead center and bottom dead center. The bore is the piston diameter, and then we have an intake valve, which is where we intake fresh air, and the exhaust valve, which is where we exhaust the hot combustion byproducts. The clearance volume is the volume formed when the piston is at top dead center. And then the displacement volume is not the maximum volume, but it's the volume between top dead center position and bottom dead center position. So another way to calculate this displacement volume would be the stroke multiplied by the area of the piston, or the circular area. So pi d squared over 4 if you're looking at the bore diameter here. So the stroke times the pi d squared over 4 gives you this displacement volume. The compression ratio is a ratio of our maximum volume to our minimum volume. So our maximum volume is the volume that is encompassed by the cylinder when we're at bottom dead center. So it's this displacement volume plus the clearance volume. And then the minimum volume is just the clearance volume. The mean effective pressure is just this fictitious pressure that we would assume or use if we were assuming this was a constant pressure process. And this mean effective pressure would be the pressure by which we could produce the same amount of work if it were a constant pressure, just the volume was changing. So P delta V would give us our net work. So this mean effective pressure is equal to this net work divided by the change in volume. And again, that's just another way of idealizing this system. So if we wanted to compare the mean effective pressures of several different processes, then we would calculate it based on the network output and the volume displacement. Auto ignition is premature ignition of the fuel when the temperature in the cylinder is raised above the self-ignition temperature. We're going to talk today about two different types of ignition systems. One is self-ignition or spark ignition, and the other is auto ignition. So gas vehicles or gas-powered vehicles depend upon spark plugs to ignite the fuel mixture, air-fuel mixture. If for some reason you're using a very low-octane fuel or your engine timing is off, then you can have auto ignition, which is where the fuel is being compressed to very high pressure and it ignites without even having the spark plug spark. Okay, this is never a good thing in an engine, and it's something you want to avoid because it causes engine knock, which is an audible noise produced. And we're going to hopefully watch a little video that will show that. That's the auto ignition. Okay. So what's happening there is the spark plugs are firing after the fuel has already ignited, and the timing is all off because the cylinder is being pushed and compressed prior to when it was supposed to. And so it causes really a lot of problems in the engine. You have a significant reduction in your power output, and it's just really not a good thing because you have incomplete combustion and it causes problems with your cylinders. It can cause fouling and things like that. So octane is added to fuel, and or additives are added to the fuel that increase the octane, and the octane is just a measure of that knock resistance. So if you do have a vehicle that has a trouble or a problem with knock, one possible solution is to increase the octane of the fuel that you use. And generally, high performance vehicles have a higher compression ratio, so they require a higher octane fuel because they're compressing to higher pressures, which can prematurely ignite the gas. So if you use low octane fuel in a sport car, you'll have problems with that. Another interesting thing is the compression ratio for a vehicle can sometimes change as it ages, which can cause knocking later in life for a vehicle. So if you have an old car that's knocking, you might need to give it a better fuel. Incidentally, giving a vehicle high octane fuel when it doesn't have any issues with knocking is just a waste of money because it doesn't really increase performance any. You can do that by having a higher compression ratio, but you can't change that once the vehicle's been made. So having a higher octane fuel probably isn't going to help you any if knocking isn't an issue in your vehicle, or not significantly. Okay, so the two types of engine, we've talked about spark ignition, where the combustion process is initiated by an actual physical spark. Okay, so this air-fuel mixture is compressed, the spark plug sparks, and ignites it. Okay, compression ignition has, instead of a spark plug, it has a fuel injector. So this cylinder is being compressed while it's fairly empty. Then the air-fuel mixture is sprayed into the cylinder, and when it's at a high pressure, then the mixture will ignite because it's at a high pressure, which then causes this mixture to increase in temperature rapidly. So that's how the ignition process occurs in a diesel engine, okay, that you have fuel injectors. So on a very cold day, it's sometimes difficult to start a diesel engine, so they use a glow plug in order to kind of heat things up a little bit first so that this fuel injection process can actually ignite. Because if your cylinders are all very cold, your block is cold, it's hard to self-ignite because an engine acts like a big heat sink in that it's a large block of cold metal and it makes it difficult to ignite that fuel. Okay, so let's look at more specific types of these reciprocating engines. The Otto cycle is one that is commonly used to model an idealized version of a gas engine. And the actual cycle consists of two strokes. So there's an intake stroke in which the piston moves down to intake fresh air and fuel. The compression stroke, where the fluid-air mixture is compressed. The power stroke, where the spark happens and the piston is forced down. That's where you get the power output in your engine. And then the exhaust stroke, where all those combustion byproducts are exhausted. So you can see here that this is showing 1, 2, 3, 4. We can look at another version and slow it down. So we can look at this steps distinctly. So we have intake, compression, power stroke, exhaust. Intake, compression, power stroke, exhaust. So the power stroke is every fourth stroke, okay? In a four-stroke engine, it's one of every 4 movements you're getting a power output. And you could like just have this on and be mesmerized and watch it all day long. It's kind of fun to do that if you're bored, which I never am. Okay. Alternately, those 4 strokes can be combined into only 2 strokes. So a 2-stroke engine is what you might find on a lawnmower, chainsaw, motorcycle. You find that amusing? 2 pokes, 2 smokes, yes, because their combustion products are a lot dirtier. Okay, so this combustion process, it's true. So the combustion process is happening at the same time that you're exhausting the gases from it. So a lot of times you'll be exhausting unspent fuel out into the environment. The combustion process is not complete because of this. However, you get power out every other stroke. Okay, so the 4-stroke cycle, you only get 1 out of every 4 is your power stroke. Here, every other stroke is a power stroke. which means that the power to weight ratio of these engines is a lot higher. Their fuel economy is better because you're getting power out every other stroke, but their emissions are worse. Okay, so most vehicles cannot pass an emissions inspection if they have a two-stroke engine. However, due to changes in the way that this occurs and the computer timing of the air-fuel mixture and keeping the exhaust valve closed a little bit longer while this compression or this power stroke process is taking place, that there are auto manufacturers that are working on two-stroke engines that can be put into commercial production because they do have a high power to weight ratio, and it is possible to get very, very high fuel efficiency rates. So something to look forward to. That's, I think, maybe one area of improvement that the auto industry can move toward, figuring out how to capitalize on the advantages of the two-stroke engine while eliminating the environmental aspects or the environmental concern. So you could watch that forever. We could also watch the animated engines version of it and slow it down if you want to see how it is. Okay, so another major difference with a two-stroke engine is the crankcase is sealed here. So in a four-stroke engine, the exhaust and the intake is usually at the top, so you don't ever have exhaust fuel mixing in with your crankcase. This is part of why many two-stroke engines actually have oil mixed in with them, is because it's within your crankcase. You have this air-fuel mixture, and then it exhausts from the top. So it's all sort of in one, and you can see how the piston itself acts as the valve opening and closing for this process. So power stroke, every other stroke, but you do have some unspent fuel being exhausted in the process. And the byproducts are a lot dirtier. Okay, any questions on those? Did you guys already know all this stuff? Yeah, kinda. Okay, good. Well, did you know this? Okay. This is the idealized version of it. So again, we're making these approximations based on analysis. So, or in order to make analysis more available or easier to do. So again, it's really an open system, but we're imagining that it's a closed system with a heat addition and a heat rejection process instead. So the actual PV diagram would look something like this, where the intake and the exhaust process is a fairly constant pressure process, but we just sort of remove that off there, and we say, okay, I'm gonna call this an isentropic heat addition, or no, this is an isentropic expansion and compression. This is a constant pressure heat addition and rejection. So again, idealizing the system. This is a good one to look at and remember these 4 steps. Take note of that. And if we perform the energy balance, we can determine how to model or use property values to analyze this system. So Q in, because we're looking at it as a closed system, is going to be equal to the change in the internal energy from state 2 to 3. And we can approximate that as C sub V times T3 minus T2. So again, the cold air standard assumption allows us to use constant specific heats. Similarly, for the heat out, we can analyze it using property values as well. And then if we want to calculate the thermal efficiency of this system, it's not 1 minus TH over TL, because that would be the thermal efficiency of a Carnot cycle. We could use that to find a maximum, but we have to actually use this Q out and the Q in. But because we're using C sub V and a change in temperature, we can use these delta T's in order to analyze our thermal efficiency. Because of some other assumptions, the cold air standard assumption that it's an ideal gas, part of it is isentropic, then we can also say that from state 1 to state 2, the volume ratio is going to be equal to this, and the state 3 to state 4, similar processes followed. Okay, so there are simplifications that we can do that allow us to make analysis again and determine temperature limits or volume ratios or heat addition, heat rejection that will help serve to maximize our work output. because that's ultimately what we're going for, is to maximize how much work we get out of this system. So we can analyze it that way. In order to increase the efficiency of this cycle, we want to increase the compression ratio. But we're limited by the onset of knock. So we can increase it to a certain point, but then we're compressing it to much higher effective pressures, which will cause auto-ignition. So there's only a certain point to which we can do that before we don't have octane fuels that are high enough octane to prevent auto-ignition. So we're limited. Another thing that we can do is to increase the specific heat ratio, but we're limited by the availability of fuels that we can use in order to operate this cycle. So those are the two things that can be done, and by and large, for four-stroke engines, they've been fiddled with and modeled and optimized just about as good as they're going to get. So it's not so much that the technology isn't going to improve as that we have found maybe the max limits of the Otto cycle when applying it to vehicle transport. Okay, so we've played this one out. The diesel cycle has been around even a long time as well. It's compression ignition, and so these strokes are very similar to the Otto cycle, with the exception that the power stroke happens as this fuel is injected into the cylinder and self-ignites. So rather than having an intake of air and fuel, there's an intake of air, and then an air-fuel mixture is injected into the cylinder. So this power stroke, again, is every fourth stroke for the diesel cycle. And although diesel engines generally have better fuel economy and have more power per stroke because you can go to a higher compression ratio, their emissions sometimes are worse. So because you're exhausting, if there's incomplete combustion in the chamber due to this self-ignition, then you may have more discharge of combustion byproducts and unspent fuel. Okay, so we could look again at the animated engines version of it. Yes?
This is a little bit beside the point, but I was wondering if you knew or had an opinion on why diesel fuel is so much more expensive than normal octane.
It's funny because it used to be way cheaper because it requires less refining. The closer you get to certain refineries, gas becomes cheaper than diesel. Sometimes further away from a refinery, diesel will be cheaper than gas. But I think it's all about tax. And my understanding is that it's environmental taxes on the diesel that have caused it to be so much higher. Right. Right. And it's more it's difficult to refine it to have less sulfur. But I think it's environmental reasons, and which is funny because diesel used to be so much cheaper than gas, but it's kind of reversed, that it's quite a bit more expensive, like 20, 30 cents a gallon more in many cases. So I think it's more to do with taxes and environmental regulations. Any other questions? Okay, so the diesel cycle is a similar model, but you'll notice here is slightly different, that the heat addition process occurs at a constant pressure, and then the heat rejection process is isentropic as constant volume as before. So we can perform similar analyses to find the thermal efficiency, determining Q in and Q out. But in the Q in process, now we're not assuming that it's still a closed system, but because we have this boundary work for this constant pressure heat addition process, then that rolls into it and looks like enthalpy. So we've done that before, where we take the boundary work and move it to the other side of the equation. That should be familiar. So we can calculate thermal efficiencies based on the cutoff ratio, using the ratio of specific heats, things like that. So if you want to look at the thermal efficiency for a diesel engine, depending on the fuel you use and the cutoff ratio, then you can play with your efficiency. So you can try to get a more efficient engine by just changing some of those things. And again, you don't have any problems where you have to calculate any of this, but it's good to understand how the property diagrams look, what the 4 steps are, how maybe the diesel cycle differs from the Otto cycle, how a four-stroke engine differs from a two-stroke engine, things like that. So we can increase the efficiency of the diesel cycle by increasing the compression ratio, and that's really easy to do because we're not worried about auto ignition. That's what we want to happen because we're injecting the fuel into the cylinder after it's already been compressed. So we can increase that compression ratio to a certain point, but then after much increasing and work to get it better, we have limited returns. So it's very steep returns initially where we're increasing efficiency significantly at lower compression ratios as we move higher. But then once we get to a certain point, we kind of level out around 75–80%, and we can't get really any better than that. Another way is to decrease the cutoff ratio, and then for a cutoff ratio of 1, the diesel cycle is identical to the Otto cycle. So decreasing this cutoff ratio essentially turns this horizontal line to a vertical line. Okay, so timing is important in an engine, and you'll notice the cylinders are not all firing at the same time, and they're not firing in order. And why do you think that would be? What would be the disadvantage of those cylinders firing in order? Momentum, right? So then your engine would be like galloping down the road as you're driving. So, so they go 1, 2, 3, 4, 1, 2, 3, 4. And that's part of the process, or part of the reasoning behind that process is that you don't want a forward momentum which you would develop, and you would have additional oscillation in the engine itself if you were firing them all in a linear fashion. So, am I hearing a dog barking? Does somebody have a dog parked in their car or something? Oh, that's crazy. There's a dog barking, audience. Okay. I just want them to feel like they're part of this class experience. So some other examples, the Wankel engine, which was used in the Mazda RX-7, it's not, I don't believe, currently in production anymore. I don't think anybody's using a Wankel, but it's another, it's kind of like a hybrid, like benefit of the two-stroke engine in that you have more of a power stroke because your intake and your exhaust are kind of happening all simultaneously. It's not a linear movement, it's a rotational movement, but it's, so it's, you know, it's another idea. And then the Omnivore, which is a Lotus engine, which this, I am also not sure if they're currently still using it, but it was like a prototype concept engine where you could on the fly adjust fuel ratios. So we can look at this interactive demo. Hopefully it will come up. Yeah, I think they've taken it down. But prior, what you could do is you could say, okay, you know, if I want to increase my compression ratio for this segment of my drive, you know, like I need a higher power output now, then you can change the fuel ratio, you can change the cylinder size. It's like all, I don't know, it's not fixed. Everything is changeable and movable. And so you can imagine the computer automation that is required in order to have an engine like this function properly, and what could go wrong if one little sensor goes out. But it's an interesting idea because you don't always need a high power output from your engine. Sometimes you need, you know, better fuel economy when you're cruising at freeway speed. So.
And I believe they stopped using that because there was a certain sensor that if it went bad, it would blow the cylinder.
Yeah.
Because the others were running higher,
right.
And it wouldn't change.
Yeah. So imagine if you dumped a bunch of alcohol into your cylinder when you didn't really want to. So. It's an interesting idea, but it's ideas like this that are outside, thinking outside the box of the piston cylinder device 4-stroke engine that we've been using since Model T times. Okay, so it is good. It's worked well, but you know there are other ideas, things we can do better. One of those directions is with hybrid or electric vehicles. For example, the Chevy Volt, which is all electric. And the Prius both use this planetary gear system where you can change whether you have a power input or a power output depending on if you're charging or not. With a Prius, there's a gas engine and an electric motor. Sometimes the motor is powering the wheels. Sometimes it's charging a battery. Sometimes the gas engine is powering the wheels and charging the battery. So depending on the needs of the vehicle, different components can switch between the power output or the power input, which is kind of an interesting idea as well. So Prius can get upwards of 50 miles per gallon. The emissions are low, and I own a Prius. I've had it for, I think, about 5 years now. I've only ever had to do oil changes. Like, nothing has ever gone wrong with that car. So my mom has one that she's had for about 10 years, and she hasn't even changed the battery yet. So I'm pretty satisfied. It's gutless, but I don't generally need to be drag racing down the streets. And I like not having to spend so much on fuel. And it really wasn't that much more expensive than the other cars I was looking at. So there's a plug for a Prius there from your hippie thermodynamics teacher. I make no, I don't try to hide that fact. Okay, so there's a lot of new technology. There are things that auto manufacturers need to do and have to do in order to stay competitive in the world marketplace, because in other countries they have made it very, very expensive to purchase fuel. So auto manufacturers in other countries are really seeking to try to maximize fuel economy in unique and novel ways. And using two-stroke engines is one of those ways, which of course has the added effect of increasing environmental pollution. But we're getting there. So if you want to go into the automotive industry, change the world, then come back and sell me your car. Okay. So switching gears now, we're going to look at the Brayton cycle, which is for gas turbine engines. So we've previously been looking at the power cycles, which are used to power a vehicle or move something generally. The Brayton cycle is used for generating electricity. This is another example of a power plant that doesn't use steam as a working fluid, but it uses gas as a working fluid. And the process for the Brayton cycle is 4 stages as well. There's compression, combustion, expansion, and cooling. And it's modeled using 2 heat exchangers, a turbine, and a compressor. So in actuality, you would have an intake of fresh air. Ooh, what is that? An intake of fresh air here and exhausting the exhaust gases, so it's an open cycle. But we're modeling this process as a heat exchanger where we just, by venting these hot exhaust gases to the atmosphere, we're just really saying, okay, we're going to assume that we've just removed heat from our system. Okay, so the model is idealized again with isentropic compression, constant pressure heat addition, isentropic expansion in the turbine, which is our power output, and then this heat rejection process also occurs at a constant pressure. And you'll notice here that this compressor and this turbine are connected. It's because some of the work from the turbine is used to power the compressor in this gas turbine power plants. That's called the Backwork ratio. We'll talk about that in a minute. So if we perform a steady flow energy balance again on this system, so the Brayton cycle looks like this on a TS diagram, PV diagram, those would be good to know. We can perform this energy balance like it's an open system steady flow device, each component of the device. So our Q in is equal to the change in enthalpy from state 3 to 2, Q out from 4 to 1. Again, we can use the assumption of constant specific heats to simplify it even further, so that we just have ratios of temperature when we're determining the thermal efficiency for the Brayton cycle. And if, again, we're assuming, making the air standard assumption that these exhaust gases are actually just air, then we can say, okay, for the ideal Brayton cycle, this is an isentropic process from state 1 to 2 and state 3 to 4. So if I'm assuming ideal gas, constant specific heat, and isentropic, then I can use these assumptions which hold true there. So this pressure ratio, P2 over P1, allows us to calculate the thermal efficiency for the Brayton cycle just using the knowledge of P2 and P1 and this K value for air, which is usually like 1.4. We're using a different gas and making the same assumptions for an ideal gas, but instead of using air, we're assuming it's something else, mostly methane or whatever it might be at a very high temperature, then we would use a different K value. So the backwork ratio is the ratio of the compressor work to the turbine work. And that gas turbine has to use, some of the work from the gas turbine is used to actually power the compressor. And in many cases, it's more than 1/2 of the turbine work is used to drive the compressor. So in steam power plants, the fraction was significantly smaller. And do you remember why that difference is? So in steam power plants, are we using compressors or what are we using? We have a turbine and a heat exchanger and a pump and then another heat exchanger, right? Sorry, I'm shining lasers at you guys. So this compressor, instead of being a compressor in a steam power plant, is a pump. Okay, what do we remember about the work for a pump? You can't put steam through it because it will ruin it. But we also talked about the equation for the work of a pump. Do you remember what it is? So boundary work is PdV. Pump work is, it has a V and a P in it, but they're not the same. VdP. VdP. So this specific volume for a liquid is much lower than it is for a gas or a vapor, right? So in a compressor, we're compressing a vapor, which means our specific volume is much higher, which means that the compression process requires a lot more work than it does if you're pumping a liquid. So gas turbine power plants, most of the work, not most, a significant portion of the work that they're generating has to go back to running the plant. Okay, whereas in a steam power plant, most of what you generate is actually used for electricity, and a small portion goes back to the pump to actually pump the fluid up to the heat exchanger. So for the same power output, the gas power plant has to be bigger. So the gas power turbines are much bigger than a steam powered turbine. So these plants require larger components and generally they're more expensive. Yes?
Why would these plants choose to use gas power instead?
So the availability of it. So let's say that it's just hooked directly to some gas field, you know, like there's a drilling operation nearby or something and the gas is just pumped readily and easily to it. Then it's easier to do that than try to get water. So maybe out in the desert or just somewhere where gas is cheap and they don't care. Sometimes is the answer. Okay, any other questions? I don't know. Maybe that's the answer, maybe that's not. I don't fully understand the energy industry. I try to, but the motivations baffle me more often than not. Okay, so if we want to increase the efficiency of the Brayton cycle, we can increase the temperature of the boiler, so the turbine inlet will have a higher temperature vapor coming into it. But again, we're limited by the material constraints or the metallurgical constraints of what we use, and it also can cause significantly more pollution to heat those gases up to a higher temperature because when they're coming out, they're still hot, and we have to put them somewhere. A lot of times they'll use a cooling tower or something to get rid of the heat, but then that puts more of the byproducts into the atmosphere. So the machinery components themselves, we can seek to make them more efficient. So we improve the turbine, improve the compressor. And then another thing we can do is add modifications. So you remember before when we were talking about the intercooling, reheating, and regeneration on steam power plants, that was in chapter 10. Well, we can do the same thing for gas power plants as well. But it adds significantly to installation, but also the maintenance and operational costs. Because if you have 10 turbines instead of 1 turbine, because you have reheat and regeneration in between the cycles, it's going to be a little bit more complicated to operate. If one of those components goes down and takes your system offline, it's a significant cost expenditure. So again, there's that balance of trying to make it more efficient, more effective, versus easier to operate and maintain. There's always that balance. Okay, so a note on grades, and I started doing this slide, but I didn't quite finish it. I'll just pull it up. So in the syllabus, the grade breakdown is given for what percentage everything is worth, or the weight that everything is worth. And I had a calculation in MU Online, but it wasn't calculating it correctly because I don't have class participation in there yet, and I don't have the final exams in there yet, because you haven't taken the final exam. So the way that it was weighting it was kind of weird, and I don't think it was accurate. So for some people, it was giving them the impression that their grade was higher than it currently is, and for some people, it was saying it was lower, that it wasn't consistent across the board. So I took that column out. But I've had several people email and say, hey, what would I need to get on the final to get a B in the class, or a C in the class, or whatever it might be. You can calculate that yourselves. So if you know your homework average, so you go through and total up all the homework points, how much you got on every assignment, take the average. Quiz average, midterm average, assuming a participation grade. So if you've been a good student and you haven't been, taking phone calls in the middle of class or something. By and large, everybody's getting full participation points. I have a little bit of leeway with that. Then you can calculate and put in, like your final exam grade and see, okay, well, what would it need to be in order to get an 80% in the class, or 70%, or whatever you're shooting for. Then you can figure out how much you need to worry or study about your final.
Energy itself is
Yes. Yeah. Homework. Yeah, so if you have golden tickets and you haven't used them yet, you can turn them in with the last homework, and I'll give you extra 10 points on that homework. So, and then those of you that used them, you used them. So you don't get the extra 10 points, but you got a non-late homework. So, figure that out. You're engineers, you know how to do math. Most of you do simple math. Sometimes it's the simple stuff that trips you up. Anyway, so this is not complete. You have to add in 0.25 times your final exam point anyway. And then you could move that to the other side of the equation and solve for x. Just solve for what you need, minimum. But anyway, I took that column out because it was too confusing to people who were like, wait a minute, I calculated it, and I should be higher than this, and so it's not there anymore. It's like a black box in MU Online, and I can't change anything that I want to change. So